Welcome back. Today we're going to be talking about something slightly different. The topic of discussion for today's video is the natural log of complex numbers. And I'll remind all of my viewers that a complex number is a plus bi, and this can be written as z, where a is a real part, for example 2, plus bi, where b is just the coefficient of our complex term, or I guess our imaginary term, where, for example, 2 would equal 2 plus 0i, obviously being a true statement there. And in addition to this, we know, or many of you may not know, but so I'll actually keep this over here, z equals a plus bi. Also, we know that e to the I theta is equal to cosine theta plus I sine theta. And what Euler thought, and I guess other mathematicians, was, if we multiply both sides by r, we thus create a polar complex term, because r e to the I theta, our complex number, is equal to r cosine theta, our real part, because for any theta we plug in, we will get a real number, plus r I sine theta, our imaginary part. Cool, I'm going to rewrite this right over here, and we're going to begin. r e to the theta is equal to r cosine theta, and I'll do another video of proving this. It's actually a super easy proof. You just use power series of e and then e to the I x. Super cool. Okay, cool. So let's start with the first one, natural log of 2, for example, okay? Would you all, no, I'll actually write it straight. I'm sorry for that. So, yeah, the first one we're going to do is natural log 2. Would everyone agree with me that natural log 2 is the same thing as the natural log of 2 plus 0i? I showed this earlier. This is just a true statement. Okay, so now is our part where we get to turn this into polar form. And you'll stick with me, you'll see why. So, if we were to plot 2 plus 0i in the complex plane, where this is our real part, this is our imaginary part, would you all agree that we'd have 2 ticks on the real side, and this right here would be 2 plus 0i, where we're going up 0i over 2. Okay, so it's kind of a weird Cartesian system, but it still works. And so now we need to think about this as more of a vector. So we need a magnitude, which is going to be 2, obviously, because that's how far out we're going, and we need a direction. So our direction in this case is going to be 0, 2 pi, 4 pi, 6 pi, and however many iterations of a circle just go around. All you got to remember is this, this, but because we're using a branch cut, we're going to stick with 0 today. So, we've determined that r, our magnitude, is equal to 2, and our theta is equal to 0. Okay? Therefore, we can now rewrite this complex number as a polar complex number, plugging it into this formula here. So now we can say that the natural log of 2 is equal to 2 e, actually it's still the natural log, of 2 e to the I times 0. And if you remember a property of natural logs, the natural log of a, b can be written as natural log of a plus natural log of b. Therefore, we can rewrite this saying that natural log of 2 is equal to natural log of 2 plus natural log of e to the I times 0. Would we all agree that any number to the 0th power is just 1? Therefore, natural log of 2 is equal to ln2 plus natural log of 1. And we all know that natural log of 1 is 0. Therefore, we have a true statement, natural log of 2 is equal to natural log of 2. Now, we'll do a slightly more complicated one. I've never done this one before, so we'll see what it turns out to be. The natural log of 3 plus 4i. Okay, so first thing we need to do is turn this into a polar complex number. And the reason we did that, again, as you saw there, is once turning it into a polar complex number, we can split it into a real part and an imaginary part. And then because of the e and the natural log and e being inverses of one another, they cancel out nicely. So, I'll continue here. We'll also do I to the I today. Actually, we'll do that instead. So, example, and this is kind of expanded on this, of I to the I power. What is square root of negative 1 to the square root of negative 1 power? Interesting, right? So, first we need to define e as a complex number. E on the complex plane sits right here, up just I plus 0 plus I, right? Therefore, we can see that our R is equal to 0. I'm sorry, our R is equal to 1 because we're going up 1 unit, and our theta is equal to pi over 2, okay? So now I'm going to define I as being equal to EI pi over 2, okay? So, now, by taking the e to the natural log of this function, because remember that e to the natural log of x is the exact same thing as x, therefore I can make that manipulation without changing the value of anything. So keep that in mind. So, therefore now we can say that e to the natural log of I to the I power is equal to e to the I natural log of I. We're getting places. Okay? So, now we can say, what is the natural log of I? Oh, well, we know that e natural log of I is just, I'll actually write it down here. So we'll start with this part. We know that the natural log of I is just equal to natural log of e to the I theta. Oops, e to the I theta over 2, right? Therefore, these two will cancel. Natural log of I is equal to I pi over 2. Cool. So now we can substitute that in here. So now we got natural log of I times I pi over 2. Now we're going to get even more interesting. I times I, negative 1. Now we can say that this is equal to e to the negative pi over 2, which means that this is equal to 1 over e to the pi over 2. And there you go. We just went to the complex world, baby. Have a good rest of your guys'